Hi synth lovers. Welcome back to my channel. This video is part of a series of videos in which I am designing and building my own DIY modular synth from scratch. As you know by now, I have chosen to create an oscillator module using the famous CEM3340 as the beating heart. It is the first module I am making, so I want to keep it fairly simple. In this episode, I will explain the design for the circuit for one oscillator. Without further ado, let's start. The layout of a CEM3340 is shown here. We will go through all the pins and find out what to do with them. We will concentrate first on the power management. There are 3 pins we need to consider for powering this chip: VCC, VEE, and ground. Euro rack has a VCC of plus 12 volt and a VEE of minus 12 volt. Can we use these? Looking at the specifications of the CEM3340, we learn the following. Positive supply voltage range, 10 to 18 volt. Negative supply voltage range, minus 4.5 to minus 18 volt. That seems to fit. However, the datasheet also specifies that maximum voltage between VEE and ground pins is minus 6 volts. This means that we cannot connect the minus 12 volts to VEE. The datasheet suggests adding a resistor between the minus 12 volt supply and the VEE pin. However, I saw another solution that looks nice as well: use a minus 5 volt regulator. And that is exactly what I will do. And this is how the schematic for the power management will look like. The two 100 nanofarad capacitors are decoupling caps. They stabilize the power supply to the 3340 in case of short dips or spikes on the power rails. They also filter out the noise that resides on these power rails. Next, we will look at tuning. These are the pins that are related to that. The voltage on pin 14 determines the scale or frequency range. The voltage on pin 1 and 2 are used to fine-tune the frequency range. The resistor network to establish that voltage is equipped with a trim potentiometer. This potentiometer is used to fine-tune the voltage per octave response of the oscillator. Another part of the scale and tuning circuit is the capacitor on pin 11. The data sheet recommends a mica capacitor because of its low leakage and temperature coefficient characteristics. Finally, high-frequency tracking is used to straighten the voltage response curve for the higher frequencies. I will explain how this tuning works in a later video, when the VCO is assembled and ready to be used. The schematics for the tuning and scaling look like this. Let's now look at the frequency synchronization inputs. There is a hard sync and a soft sync input, but what does hard sync and soft sync mean? Conventional hard sync works like this. The wave of the oscillator that is being synced is reset at every raising edge of the signal from the synchronizing oscillator. In this example, there are 2 oscillators. The first one is our synchronizing oscillator and is outputting a square wave. The waveform is represented as the red trace on the scope. The second oscillator will act as the slave oscillator and outputs a sine wave, which is represented as the blue trace on our scope. At this moment, both waves have the same frequency, and synchronization is not enabled yet. When we enable hard synchronization, we can see that the sine waveform is aligning with the square wave. The frequency does not change. When we lower or raise the frequency of the sine wave, we can see that the sine wave is being reset at every raising edge of the square wave. If the frequency of the sine wave becomes lower than the frequency of the synchronizing wave, the frequencies of both the synchronizing oscillator and the slave oscillator will be the same. The frequency of the slave oscillator will follow the synchronizing oscillator as long as the frequency of the latter is higher than that of the slave oscillator. Conventional soft synchronization works in a different way. Here the wave of the slave oscillator will change direction at every raising edge of the synchronizing wave. If we look at the data sheets of the CEM3340, we see a different approach for this chip. The synchronization is not done on edge detection, but on synchronization pulses that need to be fed into the sync inputs. Edge detection must be done by the electronics before the signal reaches the sync inputs. The hard sync of the CEM3340 reacts on positive and/or negative pulses. A positive sync pulse will cause the wave to reverse direction only during the rising portion of the wave, while a negative sync pulse will cause the wave to revere only during the falling portion. Soft syncing is only possible on negative pulses and will cause the upper peak of the signal to be reversed so that the oscillation period is forced into becoming an integral multiple of the pulse period. Since I want to create a dual oscillator module in which one of the oscillators can be used as a synchronizing oscillator and the other one as the slave. This is like what is done in the design of the Pro one. It is also described in the CEM3340 data sheets as being a conventional hard sync. The design uses the soft sync input of oscillator A, which is synced with the sawtooth signal from oscillator B. The hard sync input of both oscillators will not be connected. I will add a switch to enable or disable the hard sync between the oscillators. Next on the list is pin 15, the frequency control input, or volt per octave input. The schematics for this is a simple passive mixer. The pulse width modulation is a bit tricky. The CEM3340 only accepts signals between 0 and 5 volts. LFOs might generate signals that are 10 volts peak to peak, so, plus and minus 5 volts. Other sources claim that control voltages can also be from 0 to 10 volts. My design only takes in account the plus and minus 5 volts use case. I really don't know how the CEM3340 will react if the voltage is higher than 5 volts or lower than 0 volt. I noticed that other designs also don't take any precautions to limit the voltage to the CEM's limit. The 1 megaohm resistor between the pulse out and the pulse width modulation input is, according to the CEM datasheet, to add some hysteresis to the pulse shaper. The linear FM input circuit is based upon the one in the datasheet. There are two kinds of frequency modulation, categorized according to their behavior. As we explained in the previous episode, the volt per octave rule implies that the frequency of an oscillator must respond exponentially to an increasing voltage. If we use a waveform as the control voltage, the oscillator will modulate its frequency exponentially with that control voltage, resulting in an exponentially modulated output signal. Implicitly, our oscillator has an exponential modulation built in. The opposite is a linear frequency response. The signal sounds smoother than the exponential counterpart. Having the means to do linear FM is a nice bonus. Moving to the output signals. The triangle output has a spec as having a 0 to 5 volts signal. For Euro rack, we want to have a 10 volts peak to peak signal. So, I need to get rid of the DC component and amplify the signal 2 times. This will be done by a simple op-amp circuit. We don't have sine output, so I want to use a wave shaper to generate something that looks like a sine wave from the triangle wave. This is the schematics I want to use for the triangle and sine wave. The saw output is 0 to 10 volts. The only thing that needs to be done is to get rid of the DC component and send it through a buffer, like this. And last, we have our pulse wave that will be from 0 to 12 volts. We need to lose about 2 volts after we get rid of the DC bias. A simple voltage divider will do the trick here. Okay, now that I have the schematics clear, I will create a PCB and send it to a PCB manufacturer. It will take several weeks to get back to me. In the meantime, I will come up with other modules for my modular synth. Next on my list would be an active mixer. I will explore that in the next episode. All documentation that I have created for this series is available on my Patreon. This includes schematics and the Gerber files for the PCB designs and front panel designs. Thanks for watching. If you like this kind of content, consider subscribing and hit that like icon. Leave a comment if you have questions or suggestions. Or just to say hello. Have a nice day and see you in another episode.